How do you prevent overfitting when training neural networks? Imagine teaching a student to recognize different animals. If they memorize every single picture without understanding the general features, they might struggle with new images. That's what overfitting looks like in neural networks. When a model learns the training data too well, including noise and random details, it fails to perform well on new data. Preventing this is key to building reliable artificial intelligence systems. One way to stop overfitting is to make the neural network simpler. If the network has too many layers or neurons, it can memorize the training data instead of learning patterns. Reducing the number of layers or neurons helps the model focus on the main features rather than noise. For example, if you have a network with 50 neurons in each layer, try reducing it to 20 or 30. This keeps the model from becoming overly complex. Another effective method is early stopping. During training, you monitor how well the model performs on a separate validation set. When the performance on this set starts to decline, it's time to stop training. This prevents the model from continuing to memorize the training data and helps it generalize better to new data. Data augmentation is also very useful. It involves creating new training examples by transforming existing data. For images, this could mean rotating, flipping, or adding slight noise. These changes make the model more flexible and less likely to memorize specific details. For instance, flipping an image of a cat horizontally helps the model learn that cats can face either way. Regularization adds penalties to the model's loss function to discourage overly large weights. Techniques like L1 and L2 regularization help keep the model from fitting noise. L1 regularization encourages sparsity by pushing some weights to zero, while L2 regularization discourages large weights overall. Both methods make the model more robust. Dropout is another popular technique. During training, it randomly turns off a certain percentage of neurons. This forces the network to learn multiple ways to representing the data, rather than relying on specific neurons. For example, if you set dropout to 50%, half of the neurons are turned off randomly each time, making the network more resilient. Ensemble methods combine the predictions of several models. Instead of relying on one neural network, you train multiple models and average their outputs. This reduces the chance of overfitting because errors from individual models tend to cancel out. Bagging and boosting are common ensemble techniques used in deep learning. Transfer learning is a smart approach, especially when data is limited. You start with a pre-trained model that has already learned general features from large datasets. Then, you fine-tune it on your specific task. This way, the model doesn't need to learn everything from scratch and is less prone to overfitting. In the world of artificial intelligence applications like ChatGPT, DALL-E, and Midjourney, preventing overfitting is vital. It ensures these models can handle diverse inputs and generate accurate outputs. For example, DALL-E needs to create images based on various prompts, so it must generalize well from its training data. Similarly, ChatGPT responds to a wide range of questions because it has learned to understand many different patterns. By applying techniques like simplifying models, early stopping, data augmentation, regularization, dropout, ensemble methods, and transfer learning, developers can build more dependable AI systems that perform well across many scenarios.